Good afternoon. I'm going to give a talk with work primarily driven by Leonardo Krapp, who's going to speak tomorrow, and Pablo Benítez-Lambay, who you heard about yesterday. And the title of the talk is the title of a paper that we submitted recently, and currently under review. Is extreme instability for particle size distributions. And the spirit of the talk is going to be rather different than the spirit of most talks so far that were very broad, trying to cover many different aspects of a given problem, or even many different problems. And it's going to be a bit similar to the tone that Pablo's talk yesterday, identifying a very well-defined problem, which most of us should care about if we are taking seriously understanding planet formation, and trying to understand the implications of the results that we are finding. Okay, so the scope is rather narrow. I would argue the problem is relatively simple, but implications can be actually very far-reaching. All right, this is not a review about the stream instability. I just put up one slide to set the tone and remind you of a very basic facts that you should have in mind throughout the rest of the talk. The stream instability is, for the most part, a very local instability, and this makes it amenable, as Jake mentioned, to be studied in a Schilling box, a small volume within a larger disk. And the basic ingredients that you need is a radial pressure gradient, which makes a gas rotate slightly subkeplerian fashion, and therefore the dust particles drift with respect to this gas, and the rate at which they drift depends basically on the Stokes number of that individual particle species and the dust to gas mass ratio of that particular dust species. And these are just two plots from the initial paper, I would say seminal paper by Andrew Udin and Jeremy Goodman in 2005. And this, without being too technical, but this is going to come up in the rest of the talk, this is essentially showing you the region in parameter space where the instability works. This is a parameter space in Fourier space. These are wave numbers for radial perturbations, wave numbers for vertical perturbations, and you can see that there is sort of, to speak, a sweet spot. It's a broad regions, but that is unstable, but it's a sweet spot for the instability to work more efficiently. And this is a particular result for epsilon is the dust to gas mass ratio for the unity here, and then Stokes numbers for the order 0.1. So this tests the scale of the problem, and just in physical units, this order, tenth of a hundredth of the disk K-hat, depending on the region parameter space, and since growth of the order of in 10 orbits or 100, you get things to grow. Okay, this is not the MRI that grows on an orbital time scale, right? That's much faster. And this is in parameter space, again taking the most that grows the fastest, but now considering the parameters that are this epsilon parameter, or the ratio between dust and gas species, and the Stokes number. And again, you can see that things are unstable for broad region of parameter space, but interesting growth rates are obtained in certain regions of this plane. Okay, as I said, I was not going to be exhaustive in the many interesting and important works that have been done over the last 15 years on this subject. The worth mentioning in this context are the paper by Udin and Johansen in 2007, where they actually show that this was just not living in our minds and pen and pencil. Some people need to feel more comfortable seeing that actually you can see this in a computer, and for very good reasons. We do need the computers to go further. And then they actually show that the initial calculations that were done in the fluid approach, thinking that the dust is a pressureless fluid, indeed were recovered with numerical simulations that were dealing with actual particles. And that's a non-trivial test. I would argue that's also slightly likely to not be the case for particles that are very large. But in the regimes that we are interested, that seems to work. And then Johansen and Udin in 2007 also they studied the nonlinear evolution of the instability. And there have been other works on theoretical aspects of this. And as you know, and you have participated in this, many papers using these results to understand implications of what we know on instability for one dust particle species, and to understand how this impacts planet formation. I would like to mention in particular, I just put one paper, but it's a series of papers written by Jonathan Squire, who's here, and Phil Hopkins at Caltech, where they actually made a very important, at least for the conceptual point of view, connection, and they show that the stream instability is nothing else than one member of a broader class of instabilities that they name resonant drag instabilities, I don't know if somebody came up with that name earlier, but I'm not going to tell you much more detail of this, except for a few more words at the end of the talk, because Jonathan hopefully is going to illuminate us all tomorrow with the details. So I wanted to say, before I actually start showing you the work that we have done, that the vast majority of the work, numerical and analytical, has been done exploring one dust particle species, with a handful of exceptions that have happened much more recently, where people have begun to study what happens in numerical simulations when you include a handful or maybe 10 or 20 particle species, okay? I'm not going to discuss that now. I'm going to show you what is the first systematic study of considering particle size distributions in the linear regime of stability. This is the previous step, at least in our mind, to understand on solid footing the numerical simulations of the future for particle distributions. These works have been done by people in the room, Shunin Bai, Jim Stone, and also by the group at Lund, led by Anders Johansen, and I think the paper was led by Noemi Schaffer. All right, so what is the problem we're trying to address? Pablo showed yesterday this very simple sketch for a particle size distribution, and I have chosen to parameterize this as the epsilon dt, where epsilon is the dust to gas mass ratio, and TS here is a Stokes number. You can do this in many different ways. This is just a particularly convenient way of doing it. And I'm just going to adopt a very simple model. It's just a power law. There's a minimum Stokes number and a maximum Stokes number. And then nothing I'm going to say depends on this very specifically, and this can be generalized for whatever distribution you want, provided that it's not time dependent. If it's time dependent, we can do that in the future. There are a few details that I need to sort out. But if this is a time-independent particle size distribution, we can deal with anything you want. We have just chosen a very simple case that many people use. So this is pretty much what you need to know. If you have a distribution like this, then and you define a range of Stokes numbers with this is going to be the integral in this curve is the mass corresponding to the particles in that particular bin, and then the integral under the curve is just the total dust to gas mass ratio. Okay, so what we are going to deal with is a discrete representation of this continuous distribution for n dust species, and that is just going to be given essentially by a collection of numbers, right? The mass in each particle species and the Stokes number that you are assigning to that particle species, okay? And then you can do this any way you want, but we just chose one way to do this, but the results will not depend on this particular choice. And the constraint we're going to have is that the sum over species gives you the total mass, which is reasonable assumption unless you have some source of dust. Okay, so this is not meant to scare you, but just to show you what we are dealing with, and just to connect this to work that has been done previously. This is just the system of equations that you solve in the framework of the shielding box, continuity for the gas, continuity for each dust species, momentum for the gas, and momentum evolution for each dust species. I'm just going to draw your attention to a few terms. This is a term that is constant pressure gradient that is responsible for the gas rotating slightly lower than Keplerian. There's just the expansion of the tidal potential in the shielding box. Coriolis forces, this is a term that you should care about, and it has all the right ingredients. This describes the coupling between the gas and the dust, and this depends, as expected, so to speak, of the dust to mass gas ratio per species, the Stokes number of each species, and then the drift velocity between gas and dust for that particular species. Okay, so nothing surprising, just setting up the problem. And then you have a term here that accounts for the interaction between the gas and the dust in the equations for the dust. Okay? So this is a system of equations which is not that trivial to solve numerically. And I would say even analytically it's quite daunting. I can tell you that I was quite impressed when I learned that Leonardo and Pablo had actually found steady-state solutions for this system of equations. Because if you want to study extreme instability, you need a background solution which is in steady state. That's what Jeremy and Andrew did back in the day when they wanted to understand the model analysis. And this is a prerequisite, I would say, to do a problem that is well posed. You need a steady-state background solution. Maybe you can find that numerically, but finding analytically, I would say, is priceless, because now you have a set of equations that are close. I'm not going to write down the explicit expressions, but the solution looks quite genetically like this. the velocity of the gas and the velocity of the dust for each species can be written as a Keplerian form, plus a departure from this, which I'm not going to bother to write down explicitly, but what you should know is that the departure of the gas with respect to this velocity, background velocity, and the dust species for each dust species with respect to the Keplerian shear depends on these two functions, so to speak, that are a sum over species. And this is to be expected. So this is saying that in principle, if I have n dust species, even though each dust species is not talking to each other directly, because they talk to each other through the gas, then when you want to understand the circumstance dynamics of n dust species, you need to carry out all of them, okay? All right, but the point is that for the first time, to our knowledge, in this paper that Leonardo is going to describe tomorrow, and it's far more rich than I'm just saying right now because it's explored a new numerical technique to deal with these equations, but you will hear about that tomorrow. For the first time, we have a set of closed analytical expressions that describe the steady-state solution of n dust species in a disk. This is a non-trivial statement, and less trivial is that they actually managed to also show how these expressions look like in a global setting, okay? But I will let Leonardo maybe mention this tomorrow. All right, so now I have set everything, okay? I have set everything up. We have a steady-state background over which we can perform a linear mode analysis. I'm not going to go into the details of how to do this right now, but if you want to discuss this in detail, I can tell you later. The bottom line is that now you have a set of equations. Now you have 4 n plus 1 equations, yes? So dealing with 2 fluids, okay? 3 fluids becomes a bit more cumbersome. You want to handle 100, that becomes more challenging, okay? So it's a large system of equations, but we learn how to deal with them in a very efficient manner. So the bottom line is that once you have these equations for the background, you need to do what you need to do to perform a linear mode analysis is to perturb that background, find the equations for the perturbations, assuming that perturbations are small, linearize those equations, and then it's convenient and this system can be dealt in this way. You can work in Fourier space, yes? And then for each individual mode in Fourier space, which is identified by the radial wave number and a vertical wave number, you can solve the eigenvalue problem and then find if there are modes that grow and which ones are those, and so on, right? It has been done extensively for many instabilities, has never been done for extreme instability for n particle species, okay? So the results look like this. This is a map similar to the one that I showed you before, originally for the extreme instability from 2005, a little more fancy. There are some colors and whatnot, but in essence, it's the same. Now, I want to draw to your attention that we are going to deal with a couple of examples to illustrate a few things. So we are going to consider 2 dust distributions with equal gas and dust mass. So epsilon is order 1. And we're going to consider a range of Stokes number that goes from 10 to minus 4 to 10 to minus 1, similar to what I had already yesterday. And another one that goes from 10 to minus 4 to 1. So also similar to what people consider. And here is where the surprises stand to show. So this panel corresponds to this range, and this panel corresponds to this range. So you can already see that including, for 16 dust species that you need to consider to describe the distribution that I'm talking here, including Stokes numbers up to order unity, already changes this quite significantly, right? But I'm not going to focus on that because this in principle could be 2 physically different dust distributions. What I want you to focus on is that how this map and this map change when we increase the number of species that we are using to describe the same distribution, okay? So constant max, constant range of Stokes number, and I'm only changing the number of species in our mind to have a better representation of continuous distribution, right? What happens is that when you go from n equals 16 to n 128, this changes quite dramatically. This does as well. And when you increase this further to 512, this changes even more, okay? And then you can say, well, but we don't care that much about how the entire parameter space, because we do know that in the linear regime, early on, the mode that is going to dominate the dynamics is the fastest growing mode. So let's pay attention to that one. Here, the fastest growing mode is this one. Then the fastest growing mode, when you increase the number of species, goes here, and then it goes here. So the location changes a little bit. That may be important. The growth rate doesn't change that much from here to here. So we would say this has converged, so to speak, as we increase the number of species. However, in this case, when we go from 16 to 128 to 512, things do not seem to behave that nicely, right? You can see here the scale, the colors give you this is a decade, and then this is actually going down by almost 2 decades, okay? I'm gonna let that sink in for a second while I have water. Okay, but you can say, well, these are very 2 particular cases. Maybe there is just something very peculiar about these particular distributions. So therefore, what we did was to understand what happens with these same 2 cases as we actually keep increasing the number of species even more, right? And now we are only tracking the fastest growing mode to make things easier, which is because it's the one that we care about. So you see some behavior here that when you increase the number of particle species very slowly, which we can talk about later. But the important thing is that as we increase the number of particle species reaching 1024, then these 2 particle distributions behave very, very differently, right? This one goes to a very well-defined growth rate, whereas this one keeps decaying, yes? Evolving, I should say. It happens to be decaying, but it keeps changing, which is not usually what you expect as you are approaching the continuous limit. Just to show a check that this is the real part, which is what we care about things that are growing. This is a oscillatory part corresponding to this mode. And this one, which is not changing here, the real part is not changing. The imaginary part here is not changing. This one is changing with n in the real part, but the imaginary part is not changing. So this at least gives you some support when we saw this. Maybe there's a problem, we're doing something wrong. Just there is an n scaling that we're not seeing. This is well behaved. This is okay, but here this is a bit surprising. Okay, so then you can say, well, you still haven't explained this is a very particular behavior for these distributions, and maybe when you look at other cases, you obtain something very different. And I'm just going to show you that this is not the case. So the exercise is presented like this. We are going to consider a large number of particle size distributions in a very systematic way. And we are going to keep, in principle, the dust to gas mass ratio of each distribution fixed. And I'm going to tell you what that is going to be. And then we are going to change the number of species, everything in a very systematic way. So in your mind, what you should care about, I hope I was more or less careful. Here, we chose to, at this stage, fix the minimum Stokes number to 10 to minus 4, and then increase Stokes numbers, the maximum Stokes number in a systematic way. This is just to have some way to represent many different dust distributions, and we're able to order this in a nice plot. But what you should remember is that when I'm doing this, when we are doing this at constant epsilon and constant range of Stokes number, we are not changing the particle distribution per se, we are just changing this representation. And when we are doing that, when we increase the number of, this is just a graphical representation of what's going on here. And this is a graphical representation of that the total mass in dust is conserved, right? If I increase the range of Stokes number, then the level goes down, but the area under the curve is constant. So let me show you the first plot, and we can start doing this in a systematic way. So this plot is showing the results of the fastest growing mode that is scaled over there with color for epsilon, 10 to the minus 2. Yes? And now, with minimum Stokes number fixed to 10 to the minus 4, in this axis, we have the results for different range of Stokes number, 10 to the minus 4 to 10 to the minus 3, 10 to the minus 4 to 10 to the minus 2, 10 to the minus 4 to 10 to the minus 1, and 10 to the minus 4 to 1. Yes? It's a strange plot, but it's very, very, it carries a lot of information. And in the vertical axis, we have the number of species. So each column is just the same distribution of dust, just more and more accurately represented by adding more and more dust species. Yes? So here you can see signs of what I showed you before. But it's not the same distribution I was showing you before. But here you can see that things change as the number of species increase, and this, so to speak, stops changing. This one is changing, stops changing. This one keeps changing. This one keeps changing. Okay? So now that I spent a lot of time showing this plot, I don't need to tell you too many words. I can show you the systematic, the results in a systematic way. This is how things look when epsilon is 0.1, when it's 0.5, and when it's 1. So the thing that should strike you after everything I have said is that for a given particle distribution, the results seem to keep evolving as the number of species we are adding increases for most cases, not for all. When you have equal dust and gas masses, then here, this has not changed at all. It doesn't really matter whether you describe this with 2, 4, 6, 8 dust species, you get the same result. That's very good. Here the same happens, and here you start seeing differences. Okay? So there is a lot of information in these plots, which is very valuable, and we're going to try to understand this for some time. But all of this can be collected into one plot for you to really put things together of what we know today from the outcomes of stream instability in the linear regime for one dust species for a given mass and given Stokes number. And this is a slightly nicer plot than the version of the plot that I showed you before, but essentially the same as a function of Stokes number, individual Stokes number for only one dust species, which is okay. And this is for the total epsilon. This is how things behave. Okay? And this is what you all know. So now I can collect the results from the previous plot, and now the x-axis is slightly different because now I have ranges of Stokes number, but for the same mass. So these things should be more or less comparable. And you can now fully appreciate the dramatic difference between this plot, and the growth rate down by a factor of either 2 or 3 orders of magnitude or more. And really the only region of parameter space that survives, so to speak, is this one up here, which is relatively large dust to gas mass ratios, and also is contained only in this region. So I don't know how, I think I thought I was going to go slightly faster, but I hope you got across the main points. I can spend a few minutes trying to explain what we think is going on. And for this, we chose to deal with a simple example. Now consider the simplest possible case you can actually think about. This is fixed dust to mass gas ratio and a fixed range of Stokes number and a distribution with equal mass per bin. Yes? Equal mass per bin. This is not astrophysics, perhaps, but it's a simple example. And I'm going to do the exercise of keep increasing the number of species. So now the mass per species is going down by construction, and all of them are going down at the same rate. Okay? And now we can plot as a function of the dust to gas mass ratio for one dust species, and they are all the same by construction, the growth rate of the fastest growing mode. Yes? And now let's focus on the result first that we obtain for the distribution. Let me repeat this. It's an n particle species, all with the same mass, with a fixed total dust to gas mass ratio. And as I keep increasing the number of species, the mass in each of these species goes down. And the result is that for that distribution, the rate at which the stream instability grows is going down like this. Okay? And in green, I guess also for comparison, is the result that we obtain when we consider the particle species with just Stokes number unity, which happens to be the one that, if considered in isolation, it would be the one that grows the fastest in the range that we are considering. And the two results lie on top of each other. So this may seem puzzling, but what you can read out of these two lines coinciding is the fact that what seems to be happening is that in this case, in the distribution, when distribution is considered, actually the parts that are carrying out most of the instability, so to speak, are those with Stokes number or the unity. Yes, or unity actually. Yes, and this is for very low dust to gas mass ratios. And as we keep increasing this, the results do not coincide so well. And I can comment on this in the next slide. But here, the point that I want to make is that there is nothing strange, so to speak. What this is saying is that as the number of particle species keeps increasing, the one particle species that was going the fastest, yes, is receiving less mass, and then the growth rate goes down. Things are a bit more less trivial as you move towards higher masses. I have one more slide. Is that okay? And then this is just a summary of what I just showed you in one plot, actually including scales now. The growth rate here is going down with the square root of the mass for a given species, in this case for Stokes number unity, and this is linear, okay? And the reason I'm showing you this is because This is, we now can make a very important connection to the work that has been done by Jonathan and Phil Hopkins on restaurant drug instabilities, because what we are showing is that actually the way we are seeing the stream instability decreasing its growth rate as we increment the number of particle species, the explanation for that has already been given. This is true when the dust to mass gas ratio on the entire distribution is very low, and the restaurant drug instability theory as has been developed actually applies. However, as we actually increase the dust, the mass of the dust in the distribution, things behave differently. This is this curve, okay? And we can go into a bit more details later. I'm running out of time. But actually, what is happening now is that the restaurant drug instability theory, as it has been applied before to one dust particle species, is a priori no longer applicable to what we are doing. And the explanation is mostly that now one dust species gets out all of the rest because they are actually modifying the background very strongly, and this implies a non-trivial interaction or interference between them. And I have one more slide that I'm just going to put here for on one last statement.
I think we should probably take questions and people can read
you can
the
read
slide.
the statement.
Yes. Questions? Well, thank you, first of all. And questions, including about the last slide. Jeremy.
Well, good. You've answered your referee's report very well.
Yes.
But so this is the traditional analysis of seeding instability, which is a homogeneous background, spatially homogeneous background, which is the cleanest case, of course.
Homogeneous in the vertical direction.
Homogeneous in the vertical direction in particular. In reality, there will be some vertical stratification of the dust, considerable concentration. In fact, right. So something else. So the take home from that, especially from that last slide, is that essentially, at least at the relatively high dust to gas ratio limit, each species is on its own. It grows, or at least the dominant species grows
at the low end.
Sorry, at the low. Okay.
Yes. If I can just put it back.
Yeah.
Yes.
Square root versus the. Sorry, I don't remember. In the single species limit, as the dust to gas ratio goes down, is the growth rate linear or quadratic, or square root?
No.
Sorry,
the blue one is the low dust to gas ratio.
Well, in any case.
And square root.
So it suggests that each one of these species wants to resonate with a wave that's traveling at a different speed, and they don't interfere, but they don't cooperate.
Yes.
If there's vertical settling, there's a different regime where you get a midplane that's essentially dominated by dust, or has an epsilon of order unity. And in that case, the whole dust layer is sliding with respect to the overlying gas.
Yes.
And there's a vertical shear then between the dust enriched layer and there's a version of this, actually older, that can still occur in that case. So
yes.
Just a comment.
Okay. I appreciate the comment.
Other questions? Chris?
So at least for the steady state, I've seen that there are solutions that use an integral representation for the particle size distribution.
Yes.
Would that help you, or is that still something you...
That's a very good point. We actually thought about this. I would say that we gave up momentarily because we had a very clean way to address this problem the way we did it. In principle, it's true. One could try to actually develop a continuous approach. It was not obvious how to solve that problem, but to be completely honest, now understanding the results the way we do, I don't think that's going to help. Maybe Jeremy has some insight into this. And I even know that some theories that develop a continuous limit first have some issues that then you have to actually try to solve. So we were happy with what we are doing this way, but that could be, I don't know if you thought about this.
Sorry, what's the question?
The question is, what would happen if we were to actually, instead of dealing with discrete number of species, deal with the problem continuously? And I'm stating that even though I think that's a fruitful approach to maybe produce some insight, I don't think that what I just mentioned is going to go away. Here I can make n as large as I want.
Yeah, I don't think it would be technically difficult and probably not very rewarding. I agree.
I want to make sure that you got this point, that understand that this is being done for a limited number of dust species, which may be nevertheless very large to what you're used to thinking, but it's 1,000, 2,000. This is not yet a continuous limit, but
Okay, one last question.
yes.
I was wondering, with one species only, for epsilon equal 10 to the minus 2, we know from the models of Daniel that you cannot get this streaming, right? You need at least 2 times that. Would you say that with more species, the problem gets even worse?
I think that the problem gets worse almost always.
Right.
Yes. So, yes. Okay. Yes. So the last statement is what you take-home message, that unless you can find a way to produce monodispersed particle populations, which is what has been assumed all the time, perhaps without too big of a justification, the scope of the streaming stability as we know it is going to be narrowed down profoundly. Because if we actually need to account for particle distributions, which I think most people would argue is a way to go, given the observations we now have access to, then we have to think about this problem in new terms.
Thank you again.